Well, good morning to all of you. Now, today we will start on this power quality, the second lecture. It is on power quality standard and monitoring. Well, the outline of this lecture or this presentation is, we will start from introduction, then we will go for start of state of art on power quality standard and monitoring. I will like to cover power quality terminology, then power quality definition, then we will go to power quality standards, talk about power quality monitoring and the different instrument and equipment are available from different manufacturer, and then we will give some of the numerical examples which really will make you this course interesting, followed by summary and references like. Well, the objective we put it for that, explaining the terminology of power quality, because you have to quantify the power quality, and then we will like to talk about indices of power quality, then the power quality standard, then the monitoring of power quality and power quality assessment like. Well, to start with, there has been exponential growth in interest in power quality in last quarter century, which may be witnessed by published literature in terms of research publication, text, standard, patents, application notes from different manufacturers for different equipment of mitigating the power quality. A number of standards have been developed by various organizations and institutes, which are to be enforced on the customer, manufacturer and utility to maintain the acceptable level of power quality. Apart from these factors, various techniques and instruments are also developed to study and monitor the level of power quality pollution and their causes. And many industries are developing number of instruments, recorder, analyzer to measure and record and analyze the data at the site or in the research laboratory to quantify the kind of problems at different places like. Well, we would like to talk of first on the state of art on the power quality standard and monitoring. Well, a number of standard and benchmarks are developed by various organizations such IEEE. I hope you are aware with the IEEE Institute of Electrical and Electronics Engineers, which at the moment consists of more than 40 lakh documents, and lot of standards they have developed for different purpose, and on power quality also they have a number of standards. So, the very main standard we like to introduce and talk about what really are important. It is very difficult to cover all the typical standard here like. The another organization which is like a commercial organization called IEC in short, and we call it International Electrotechnical Commission, virtually placed in Geneva, and they have developed lot of standard typically like. So, out of these two organizations, these two standards such as typically IEEE 519 from IEEE side and IEC 61000 on the they give the permissive limits on the deviation, distortion in various electrical quantities such as voltage, current, power factor, and continuous monitoring, detecting, recording and leads to prevention for power quality problems. Like we have to quantify first and then only we can think about. So, this is a typical list of some of the standard on various issues of power quality. They are not all, it is only the few standard, we can't cover all. So, very popular standard which is IEEE 519. It was originally developed in 1981, modified in 1992. This is recently also modified in 2014, and the standard title is, which is around 100-page document, recommended practice and requirement for harmonic control in electric power system like. There is another, so this standard is typically what the standard give it, you can download this standard from IEEE Explorer and you can go through this. So, they talk about like not only the benchmark, but they give some of the practices also which you can probably meet for different applications like. So, another standard is of this IEEE standard 1159, of course, typically developed in 1995. This is the recommended practice for monitoring of electric power quality. So, this is something like they define what are the different parameters and what is the method to different kind of instrument or equipment to record or monitoring this power quality. And another standard of IEEE 1100 which are developed in 1999, recommended practice for powering and grounding sensitive equipment. If you do not ground properly these electronics equipment, certainly they will have a noise and the disturbance like. So, grounding is also become very important like. and another standard of IEEE standard 1250 developed in 1995 typically guide for service to equipment sensitive to momentary voltage disturbances, and IEEE standard 1366 electric power distribution reliability. So, these are indices like, so these are the very important standard among the probably might be more than 50-60 standard in IEEE, because even IEEE have developed a specific standard for specific application also, but these are in general nature. Like the another organization which we already talked about, IC 61 International Electrotechnical Commission from Geneva, commercial standard, and they have this standard name called 61000. There are different parts of this standard, probably 15-16 part like and these are typically we have just talking about probably few parts only here of typically part 2 to compatibility level of low frequency conducted disturbances and signaling in public supply system, and another standard 2-2-4 compatibility level in industrial plant and low frequency conducted disturbances, and IC 61032.2 limits for harmonic current emission equipment input current up to and including 16 ampere per phase. So, this is relate basically for the all the equipment of single phase, because from single phase supply if you talk about either 220 or 230 volt, the maximum socket you might have seen of 16 ampere socket there. So, this standard made for that purpose only, that what the load you can have up to 16 ampere. They give a different kind of limit for very small rating, like typically starting from few watt like 20 less than 25 watt, more than that or so. The another standard 61004-15 flicker meter functional and design specification. So, different standard they go on introducing, and based on the different instruments start coming or meters coming, recorder, monitor they are coming. So, they go on introducing different functionality into that. The another European standard of 5016 is the 4 voltage characteristic of public distribution system, like also. So, these are very important. Like if you really want to go, there may be more than hundreds of standard in the power quality for quantifying and recording for different purpose like Well, we like to talk about again power quality problems in little bit in detail. So, first we have a voltage based power quality problems like power frequency variation. Voltage based power quality problems in the sense what the power quality problems are in the typically normal grid, like you have because supply is available all the place. So, what problem can be there in the power supply. So, one is the power frequency variations. You might have observed the frequency variation in that. Earlier it was more in India also, now it is little less. The reason being earlier could have been that we are not connected the any kind of the cost associated with power frequency variation, but now we have associated, because the throughout the world there is a concept coming like of a smart grid and other features. You can think about like frequency increasing means we have a generation more on the network connected to network. So, you have a more generation, more power, but certainly loads are less. So, that is a indirect reflection on the frequency, and when frequency go down it means the generation is less, load is more. So, now it is related to the the cost of generation, cost of transmission as well as distribution or utilization, that if the frequency goes up you make the electricity cheaper, and if frequency goes down you make the cost of electricity costlier. So, certainly like in the environment typically of course, in India we do not have a for the consumers the different rates of electricity, but of course, there are different rates. Up to 200 units you have a different rate, than more than that, and bulky consumers like IIT we have a around 10 rupee 25 paisa. So, these are the different rates, but what but these rates are not in India depending upon the time variation. Of course, for distribution company, I was talking about both the distribution company in Delhi, they say that they are purchasing probably electricity in the daytime in the summer peak around 9 rupee 50 paisa and selling around 10 rupee 25 paisa, but in winter they are going to sell by only typically 2 rupee 50 paisa or so. So, this cost variation is not reflected to public, but it is already there in the typically for the utility. But if you go to other countries, many countries like Australia, Europe and America, they correlate this cost with the certainly with the frequency like and with that certainly you will be able to automatically regulate the indirectly here also regulate when the regulatory commission came. So, they relate something with the generation transmission and going to be up to the distribution company and that really regulated the frequency back. Now, we do not have a frequency variation hardly even 1% means 0.5 hertz above or below. Earlier otherwise it was, I mean limit was standard to say 3%, it was violating even the 3%, but this regulatory board when it came and they introduced this with the finances, then this frequency variation in India also now reduced, and we are, because the reason being the many, the typical equipment in the different power stations, generating stations, we are of course have a equipment coming from installation from abroad, and we have to bypass their protection, and there was a danger and other issues related to operating network also and those generators. So, those problems were there, but after introducing this regulatory commission and these tariff related to with the frequency variation, now this problem is also reduced, and frequency variation is not really too much now, even less than 0.5 hertz variation you will see. So, this becomes very important. The another is the voltage swell. We discussed it even the previous lecture also, that if you suddenly throw the load or you make a capacitor switching, so voltage try to go up for very short period, for few cycles it goes, so that we call it voltage swell. I will just show you, discuss little later in more detail. And then the harmonics and interharmonics, voltage unbalance, flicker, voltage sags and monetary interruption, and of course, the transient line. So, these are voltage power quality problems, and we will talk about of course, current based power quality problem. This is first related to the reactive power, burden on the system. So, we have to compensate for that, or you have to generate the reactive power. Fortunately, you can generate the reactive power locally also. I do not know whether you are aware or not, that we can generate the reactive power not only typically from capacitor banks and the inductors, but we can generate the reactive power by active devices also without using the much energy storage devices like the Japanese group like Akagi group, especially who is pioneer in power quality, they even in 1984 they reported that with the switching devices, you can generate the reactive power without having energy storage devices. Like I will like to talk that also little later much in detail, of course, when we come to DStatCom and others. Like another problem is the voltage regulation problems. Like voltage regulation means when you draw really like a lagging power factor load, you might have seen, then your voltage regulation goes down, voltage goes down, and when you have a leading power factor, voltage try to go up even in the distribution system, and that given in a birth that okay, with the help of typically your capacitor panel, you can improve the voltage profile also, but you can understand the load nature is very difficult to control. The consumers are keeping different kind of load in terms of like a maybe lagging power factor load, leading power factor load. In general, it is lagging, but now it becomes more complicated when you have a harmonic producing load. Like so the voltage regulation problems also become severe, and then the current harmonics. Because I was discussing in previous lecture also, you draw a lot of lot of loads draw the current harmonics, and these loads are basically we call it classified. Later on we talk about like a nonlinear load, but you cannot avoid those loads, because the many process we require such a solid state controller into that. And then you have a load unbalancing. We have a load unbalancing on 3-phase system. Even you might have design or probably let us say plan it for balance load on the all 3 phases. Take a typical example in a hostel. You might be giving for 3 different wings of the hostel the 3-phase supply for one phase from one wing, another phase another wing, and third phase another wing. By design you might have made the load balance, but you can't force the consumers to keep all the time load equal all 3 phases, and that causes certainly the load unbalance. Like because most of the domestic loads, or you can see residential loads, even a commercial building loads are like a single phase loads. So, that causes the reasonable unbalance in the your typically in 3-phase system, that cause load unbalancing, means all 3 phase currents are not equal all the time, and their nature in the sense their power factor, their harmonic level, that is also different. Like so that also causes the voltage power quality problems, along with of course they cause the increased losses also in the typical distribution system as well as in the transformer. Like and then the neutral current. Neutral current I explained in the morning also, when you have a 3-phase 4-wire system. Ideally if you have a normally what we were saying earlier, that maybe a one phase load may not be there, or only you are drawing single phase load. So, maximum the current in the the neutral can be only equal to that phase current, that can be not more than 33%, means 1/3 of that typically. So, that is the reason the conductor earlier was designed only typically rating of the 50%, we call it 50% core. But now when you have even all 3 currents equal with the high order of harmonics on line to neutral connection, and there have been we will discuss sometime, there have been a case study also of neutral conductor bursting in high rise building, where you have a lot of computer loads, as well as you have a like a lighting loads which consist even the magnetic ballast earlier in the fluorescent lamp. Even today LED lighting also same situation is there, that you might have excessive neutral current. I mean, look into a 100-story commercial building, like of course may not be having so many building in India, but look into the country like a Singapore, which is only vertical. I mean, you might have a 100-story building. So, I mean, you might be having neutral conductor and phase going to in the building at different floors, and that neutral conductor it was put off only 50% cross section, but you are forcing the current go to into 150%, and neutral conductor got busted like, and you are not able to see that lot of computers were failing. I mean, this is typically the survey done in 1990 around or so. So, that neutral current problems is also very severe. I mean, typically. So, we classified I mean current based power quality problems like with the another classification, like we have a 2-wire system like a single phase, we have a reactive power and harmonics. If it is a 3-wire system, along with the reactive power and harmonics, you have a typically unbalance also like a negative sequence. I mean, you might be putting like a line to line load on a 3-wire system, also like a traction load, furnaces load, they are like only, and of course, we design some way, but still I mean there may be operational unbalance there too. Similarly, I discussed with the another is of course neutral current severe problem like. About this voltage sag, I mean voltage sag as you can see from this figure also, a decrease of nominal voltage between 10 to 90% of the nominal RMS voltage, and at the power frequency for a duration from half a cycle to 1 minute, and you can clearly see even voltage is depressed, how it is here and how it is here it is reduced for some period, and how the RMS voltage is reduced. So, this we quantify like as a voltage sag, and certainly you can understand if such a typically sag is there, then the protection of your many sensitive equipment may operate, because voltage is not within the limit like. So, it can call as a interruption in the process or disturbance to the many process. I mean those processes stop functioning or stop your affect your protection system also like, because protection may operate like. What are the causes of this voltage sag? The first cause normally are the faults on the transmission or distribution network, faults in the customer installation, and connection of heavy load and start up of large motors. Like you might have seen when we start very large motors, I mean this problem is very common, or you might have seen in the typically semi urban areas. I mean in the evening when sometimes water supply was not common, and water supply comes only for limited period, and most of the consumers they switch on their booster pump simultaneously, and that is normally the evening, and you might have seen the reflection on the lighting system sometime that UV light were stopped working. So, that was certainly what happens, those all the even a single phase motor is of a small rating, the booster pump they people start it, they large current, they draw the large current at starting, and the voltage dips is there, then that causes only momentary, you can call it the dip in the voltage, because the starting of the motor takes hardly few cycles like, which comes under the category of the voltage sag. So, such sag can be I mean practically there in many situations, or even you can have a large rating starting even the. So, we have to design typically this large rating motor, or typically even a different starter schemes you have to use it in large rating motors to reduce the starting current or starting ingress current. So, that if large current is drawn from the distribution system, because the I mean even very small impedance can cause a substantial voltage drop at the point of common coupling where most of the loads are connected. So, you are causing a reduction in the voltage. I mean when you are starting your motor, you may not be affected much because short period your motor is not affected, but other consumers are affected because of this voltage sag or voltage dip like I mean also. Well, what is the consequences which I am mentioning? Malfunction of your microprocessor based control system like your programmable controllers, programmable logic computers or personal computers, programmable logic computers, adjustable speed drive, and that is the reason for PCB normally use the UPS. I mean those things will not affect like your computer, otherwise computer may trip for the short period. I mean you know, and that encourages a lot of UPS for every computer we are using almost like a half kVA UPS or so, or programmable logic controllers or adjustable speed drive. I mean their protection operate. If you have a typically a sag for CV cycles or for typically which can go even for a minute or so. So, that may lead to a process to stoppage or interruption in the process, like protection may operate, or tripping of contactor and electromechanical relays in the process, and disconnection and loss of efficiency in electrical rotating machines like well, the another I mean typically the voltage swell, and this is just opposite to the voltage sag. The momentary increase of the voltage at power frequency outside the your normal tolerances with duration for more than one cycle to typically less than phi seconds like, and you can just see here in the figure that for the red portion a couple of cycle voltage are going beyond the 100% limit, otherwise with the green it is within the. Similarly, you can say on the right side that the RMS voltage increases for only phi cycles like or phi cycles may be because it can be phi seconds in phase second, because in 1 second you have a 50 cycles typically. So you might have a several, typically you can call it if it is a several seconds or phi second. So it means maybe for even 100 or 200 cycles also. So that's we call it like a voltage swell. Well, why it is there? What are the causes for of voltages? Just like a start and stop of heavy load. You just starting the heavy load and sudden stop the heavy load. So certainly voltage will try to go up, or poor dimension power sources or poorly regulated transformer. So that's the really causes like, or typically the switching of your capacitor banks. Or even many cases like energizing the such kind of the equipment like, and consequence of this voltage sag is the flickering of lighting and screen, and sometimes the damage or stoppage or damage of sensitive equipment like. So that is how now you can think about micro interruption. This is a total interruption of electrical supply for a duration of phi millisecond to 1 or 2 seconds. 2 seconds means like 100 cycle. You can just see 300 milliseconds. It is only part of the 1 second, but it consists of around 15 cycle. So if it is such an interruption there in the supply, you will find, you might have seen sometimes supply goes for very short duration, and that cause micro interruption, and but causes the lot of process even to stop like. If it is few seconds or like a 1 or 2 seconds, then lighting system also affected like, also you might have seen like. Well, what is the causes of micro interruption? Opening or automatic reclosure of protection devices, insulation failure, lightning, and typically of insulator flashover. Consequences of these micro interruption and tripping of protection devices, loss of information and malfunction of data processing equipment, and of course, stoppage of sensitive equipment such as adjustable speed drive, personal computers, and programming logic controllers like. So, they are affected because they use lot of solid state control sophisticated component, electronics component, and the protection is very sensitive to them. So, their protection can operate, and that cause all these equipment to almost like a stoppage like also. Well, long interruption, which is very common in country like India. The total interruption of electric supply for greater than 1 to 2 seconds. We have an interruption, you can just see voltage, nominal voltage there, and there is an interruption and voltage goes 0 almost like. So, it is very common, and why we have a majority of people keep the typically with the sensitive equipment like computer, you keep the UPS, as well as in domestic applications also you keep domestic inverters like also. But of course, now the quality of power, especially urban area, it is okay, but still if you go to semi urban area or you go to rural areas, still the same problem, electricity comes only for few hours. It is not continuously for 24 hours. It becomes the news also in some of the states. If electricity start coming out of 24 hours, electricity start coming like 19 hours. So, even our typically the, let us say, the rulers, they talk about we have done very great job that we are providing the electricity like a 19 hours out of 24 hours like. So, this is very common in a country like India, you can think about like. But how it causes the problem for you, that's become. So, what is the causes of long interruption? Like equipment failure in the power system network, some fault could have come, or storms an object like a tree, car, etc., striking like on poles and fire, or human error, bad coordination of failure of protection devices, and consequences of long interruption is stoppage of all equipment like. So, it really affects like. So, this all comes under the umbrella of your power quality. And like a voltage spikes, so very fast variation of the voltage varies for its duration from several microsecond to few millisecond, as you can just see. On the voltage there is a like a, because of capacitor switching, and you have a just voltage tangents okay, here, and then how it is reflected in RMS voltage spike, you can just clearly see. This is typically in AC system, this problem is very common. You can, I do not know whether you are aware with the concept of like a typically of doubling phenomena. I mean, even if you switch on the inductive load or capacitive load, and if you are not switch on at the right instant of time, at the time of peak voltage where there is a current either of capacitor or the capacitor current in the steady state current of the capacitor or inductor is supposed to be 0. If you are switching on any other period, the voltage across capacitor also try to double it, or the current in the inductor or flux try to double it. So, that we call it doubling phenomena, and that cause the really the inverse current or inverse typically the voltage doubling across the capacitor and doubling of the flux in the inductor. And when you have a doubling of the flux in the inductor, then you can think about what will be, and that phenomena very much observed like a inverse current in the transformer, like on switching on. So, if you have not switched on the transformer at right instant, the inverse current may be as high as maybe, I mean, even many times we observe it. Even the one manufacturer of a stabilizer come to us, I do remember 25 years back. I mean, like he was putting relay on the primary side also. Normally the relay and stabilizer were put on the secondary side, but he put on the primary side, and the I mean the form basically stabilizer is nothing but the kind of auto connected transformer, and when supply got interrupted, suddenly switch on this typically a kind of magnetic circuit with the kind of transformer. There was a inverse typically a current which was going, and you can understand the MCB was very sensitive. I mean, it was 4 kVA stabilizer like a 16 ampere, but the current jumped to more than 100 ampere, and you can understand you just use this stabilizer for AC, and at the midnight around 2 o'clock your AC stopped working. You have made an investment in the AC as well as you made an investment in the stabilizer, and it stops, and you become like a sleepless, like so you bound certainly on the stabilizer person why it is happening, like so they came to us, we have given a very cost effective solution. I mean, just you not to allow the circuit to open even under the such a kind of switching in the circuit, like also. Well, the causes of voltage spikes are like a lightning, switching of line or power factor correction capacitor, and disconnection of heavy load. Like, and consequences of these voltage spikes is destruction of component and the insulation material, and data processing error and data loss, and electromagnetic interference, like well, you can call it like what is the meaning voltage fluctuation. So, oscillation on voltage value, amplitude modulated by a signal with a low frequency, and that is virtually you can call it like a voltage fluctuations, like, and you can understand that there is a low frequency, I mean, which you can call it the load is varying in a manner that the low frequency at very low frequency, and that frequency get reflected in the current, and certainly it reflects it because this current flows also into the typically in the your distribution system, and the drop in the distribution system also changes. So, point of common coupling voltage also change with the this low frequency variations, like also. So, then the typically the causes of this voltage fluctuations are arc furnaces, the frequent start stop of electric motors, or like instant of elevators, I mean like, or oscillating load. You might have seen a lot of oscillating load, I mean like people are flooring and all that, and consequences of these voltage fluctuations are most consequences are common to under voltage and flicker of lighting and screen, like then another is a typically like a voltage notching. I mean, on your sinusoidal voltage there is a notching, and you understand why this notching, and this notching certainly is nothing but it can be analyzed that you have a higher order harmonic along with the typically on the fundamental voltage, and how why it is there is because we will talk about is a thyristor converter with the source impedance. If it is there, then during that period you have a such notches, or oscillatory transient, or you have a impulsive transient, like also. Then voltage unbalance. So, voltage unbalance we will talk about later why it is there, but voltage unbalance is a 3-phase system. The 3 voltage magnitudes of the phase or the phase angles difference between them are not equal, as you can see here. I mean the red blue, you can call it red, blue, green, all the magnitudes are not equal. So, their magnitude are unequal, means you can analyze this as a unbalanced voltage as a sum of like your positive sequence, negative sequence, and 0 sequence, like as you can see in the phasor diagrams, like. So, any that is a kind of unbalance, and well, why it is there? Large single phase load, which we talk about like induction furnaces, which are of quite large rating, like maybe up to 500 kilowatt. I mean the induction furnaces is like virtually a single phase load. We try to balance out, I hope you remember that we use normally the Scott connection for that, and you get a 2 single phase supply isolated, and you can connect to 2 different furnaces, and both furnaces draw the equal load, then it get reflected like a balanced load. Is virtually you are converting 3 phase to two phase, but two phase are isolated. So, you can feed two separate, you can call it like a furnaces like, but you can't guarantee that both the furnace load will be equal all the time. So, that get reflected certainly unbalanced current on the. Similarly, like a traction. Traction also we have a single phase traction like a 25 kV line, you might have seen the single phase line. So, it is also taken from line to line on a your traction substation, but it is a single phase load on the three phase system like. So, that also can cause the voltage unbalance like. We design traction substation in the railway as well as in metro, so that the loads are equal on all the three lines, line to like A, B, B, C, C, A, but operationally you cannot make sure that in all the zones equal trains are running or equal metros are running. So, that causes typically you can call it like a unbalance, or you can call it single phase load, and incorrect distribution of loads by three phase of the system like. Might have designed, but certainly it is not guaranteed that all the time all the consumers might be keeping equal load on them. And what are the consequences of this voltage unbalance? The most affected loads are the three phase induction motor. I discussed already in previous lecture also, I can again explain it. You can understand if there is a 1% voltage unbalance, it causes 5 to 7% current unbalance, because you will have a 1% negative voltage and the impedance for negative sequence or backward field is virtually lesser than standing still impedance, which is 1/6 or 1/7. We call it now, say you have a starting current 5 to 7 times. So, 5 to 7 times is nothing, but you can call it depending upon the motor parameter, your block rotor impedance is 1/6 than full load running impedance. So, if your impedance is and backward impedance is further lower in the sense, because in starting your R2 rotor resistance by S is 1, but for backward field it is R2 by 2 minus S. So, it means it is further R2 by 2 in place of R2 only. So, it means the impedance of the motor for backward field is much lesser than what you are having positive sequence running motors, like maybe 5% slip or say maybe 3% slip or so. So, that causes certainly your negative sequence current to amplify like a 5 to 7 times. So, if you have a 3% voltage unbalance, there is a possibility you might have a typically 18% unbalance, and that is the reason 3% only voltage unbalance is only permitted 3%. However, voltage variation is permitted more according to standard, and this is the reason, because otherwise there will be a very excessive circulating current in the rotor bar of squirrel cage induction motor and cause the rotor heating. Like including it has a very robust rotor, but that will cause the losses and increase in the efficiency. Typically in the even induction motor which are ideal 3 phase motors load, but they react to this unbalance like also. Well, another is like a superimposing of high frequency signal on the waveform of power frequency. You can just see the noise is typically imposed on fundamental frequency, and why this is imposed? There are many reasons like electromagnetic interference, improper grounding may also cause maybe a cause, and consequences is disturbance on sensitive electronics equipment and may cause data loss and data processing errors also like. So, well, so those were like you can call it voltage. The another is like a typically harmonic distortion, which may be for voltage waveform or current waveform. So, you can just see as a non-sinusoidal wave shape, like it does not matter for voltage and current, like I see the black waveform. So, this black waveform it is a quite non-sinusoidal, and which may be a practical waveform, maybe of typically in some of the mixed load, and it consists like a fundamental which you see the gray line. You have a third harmonics, you have a fifth harmonics. So, any non-sinusoidal waveform can be analyzed by Fourier analysis. You might have studied the Fourier analysis in the basic circuit of your basic circuit. So, it can be analyzed equivalent to, but these harmonics you can understand maybe very different nature. So, these harmonics will certainly cause the main work done by in your load is by only fundamental current like or fundamental voltage, but these distortions certainly will increase the losses either for typically in the even a distribution system as well as in your load also. If you are fitting this, let us say for your motor, then certainly the harmonic current will flow into the motor, like because the harmonic voltage are there, and that harmonic current may cause not only the losses, but may cause torque pulsation, noise and vibration, those physical phenomena in the motors. Similarly, it may happen even the losses, additional losses in the transformer if it is in the load current like also, or even the voltage also will have, because high frequency component of voltage are there. So, that may increase even the core losses also in your transformer too also. So, that is typically the harmonics. So, harmonics have a very important role especially in power quality like because I mean any non-sinusoidal, because we are dealing a lot of non-sinusoidal waveform. We will talk about little later about that more. And you can analyze this kind of distorted waveform which you see on the right side, that you, I mean if you analyze by Fourier analysis, you might have a fundamental, because it is symmetric about x axis. Okay. How much is the waveform x axis means how much is the waveform on upper side, it is same on the lower side. So, you have a like a fundamental, then third, you will have a, you will not have a then typically even harmonics. So, you will have a odd harmonic, and odd harmonics after fundamentally the third and fifth also. And you can just see how the third and fifth harmonics, and finally, even adding a third harmonics, how this waveform get disturbed. So, third harmonics may be in the phase which make a peaky waveform, third harmonics may be out of the phase which may reduce from the peak, so it can be flat waveform. I mean towards like a typically kind of a square kind of waveform. So, third harmonic, whether it is in phase or out of the phase, makes the distortion of different nature, and this both kind of distortion are available in different equipment. If we talk about, I was talking about like a diode rectifier with the capacitive filter and then load, you will get this kind of peaky waveform. But if I am drawing, let us say, but if this peak waveform is drawn by diode rectifier, the voltage, when you are drawing peak current from the voltage, you will find the voltage will become flat at the input. It will reduce because the impedance is there. So, somehow I mean it will get in compromising situation, that voltage reduces and current increases, like I mean. So, distortion it will cause in the current voltage also, current will cause in the voltage virtually, and that is exactly happen if you are operating the transformer, like even a single phase transformer, you might have seen the magnetizing current, that waveform is similar to this, like, but that might be causing certainly the voltage distortion at the point of common coupling, because there will be some drop in the feeder as well as some drop may be in your typically block loader short circuit impedance also. So, at the point you will find some distortion in the voltage positively because of this, like depends on relative value of your source impedance when you are really running the transformer at no load, like, and that is the reason we have a experiment, like typically in first year BTech itself of your getting a typically a recording of no load current, and this is the waveform typically of switch mode power supply. I mean if you talk about around 20 years back, what was the switch mode adjustable speed drive, I mean of typically. So, voltage waveform is very quite good, but if you have a like a 3-phase diode rectifier with capacitive filter and then you are using adjustable speed drive, in the sense like a 3-phase inverter induction motor drive, you are doing the two notches, like I mean like typically this current could have been like a 120 degree duration, but it can't be 120 degree duration because you have a capacitive filter. Okay. So, you might have seen that in 3-phase diode rectifier with capacitive filter, you will have a 6 ripple in the voltage. So, when the voltage, and you have average voltage which is across the capacitor. So, when your line voltage will become more than your capacitor voltage, then only you will be drawing the current from line to line segment, and you will find two segments, because there are out of 120 degree there are two segments of 60-60 and both have a separate peak, and you will find this kind of current depending upon the value of capacitor and the load. If capacitor is high, you will get this kind of wave, capacitor of higher, then certainly they will suck the energy very quickly from the 3-phase mains, okay, and you will get this kind. But if load is more, capacitor is less, then you will get a certainly maybe middle notch can be reduced it, like. But you can understand with this practical waveform, you have a total harmonic distortion of this current waveform around 78.3%, like I mean also. So, this will cause substance, I mean which will be here, third harmonics will not be there, it will be the fifth is the lowest one, then you have a seventh harmonics, like, because in 3-phase system tuple will not be there. So, you will have a typically 6 and plus minus 1, so 5th and 7th, and then it will be 11th, 13th, that kind of harmonic pattern will be there in this waveform also. We will talk about little later, but this is the practical waveform of your 3-phase diode rectifier with capacitive filter and feeding a variety of the load, like whether adjustable speed drive or any other load, like also. So, then we of course, will like to discuss the power quality terminology, like also. So, there are many topology, I already mentioned it in different standard or different instruments, okay, or monitoring, recording, how to monitor, how to record the power quality issues. I mean these standard also talk about the limit on them or to prevention of them. So, certainly they have to define all the terminology for power quality. So, the first is the flicker, I mean the impression of the unsteadiness of visual sensation induced by a light stimulates whose lumens or spectral distribution fluctuate with the time, and you see the flicker. I mean, either it is like a typically your connection breaking, or you might have seen in the welding kind of all the flicker like. And then of course, we talk about fundamental component, like a fundamental component is nothing but component of first harmonics, 50 hertz or 60 hertz of the Fourier series of periodic quantity. And imbalance, it can be in voltage and current, might be out of 3 phase. So, ratio of negative sequence component by positive sequence expressed as a percentage, and we like a typically define the, it can be like an example like in maybe voltage or current, like impulsive tangent, a sudden non power frequency change in the steady state condition of voltage and current, and that is an interactional in polarity, and we call it like a primary either positive or negative. Instantaneous quantity, when used a quantity duration for short duration, like RMS variation of a modifier refers to a time variation 0.5 cycle to 30 cycle of power variations like. Then interharmonics, a frequency component of periodic quantity that is not an integer multiple of the frequency at which the system is operating. So, it kind of like a 2.5 or 2.5 times, 3.5 times, okay, like a half, maybe in cycle converter you will see such kind of, I mean, those have been a burst converter, and you just see such kind of harmonics also, because load may draw any kind of the current like. So, you can't control, I mean, over the fundamental you might have other harmonics like. And long duration RMS variation, variation in the RMS value of voltage from the nominal value at a greater than 1 minute. So, term usually further described as using a modifier indicating the magnitude of or voltage variation under voltage over voltage, and so this is required for defining those voltage interruption. And momentary interruption, type of short duration, we already discussed it earlier, variation and complete loss for a typically even a reduction or of maybe 0.1 per unit for more phase conductors for a time period of 0.5 cycle to 3 cycle. The RMS variation, a term defined for to express the variation in RMS value of voltage current measurement from the nominal, and typical example with the sag swell momentary. So, this is required for quantifying those like. And short duration RMS variation, a variation in RMS value for voltage and current for a time less than greater than 0.5 cycle, but equal to less than 1 minute like. So, when the RMS variation in voltage, it is further described using a modifier indicating the magnitude of the voltage variation like sag swell interruption, and possibility modifier indicating using the duration like instantaneous, momentary and temporary. So, in those we use this terminology. And sustained interruption, a type of long duration RMS voltage variation where the complete loss of voltage less than 0.1 per unit of one or more phase conductors is for a greater than 1 minute. And temporary interruption, a type of short duration square wave variation where the complete loss of voltage or more than one phase conductor for time of 3 seconds to 1 minute like. Then the voltage change, a variation of the RMS voltage or the peak voltage variation between two consecutive levels sustained for defining but unspecified duration. Then voltage fluctuations, a series of voltage change or cyclic variation for a voltage envelope. And voltage interruption, the disappearance of supply voltage for one or more phases is usually qualified by additional term including the duration of interruption like momentary, temporary or so. And waveform distortion, a steady waveform from an ideal sine wave of power frequency principally characterized by a spectral content of the deviation like. So, those were the some of the terminology, but for standardization, purpose of standardization, following additional term and definition are also used in the power quality like accuracy, and for the recording equipment like the accuracy of indicated or recorded value is expressed in terms of ratio of error of the indicated value to the true value, and is usually expressed in percent. Calibration, the adjustment of device to have a design operating characteristic and subsequent marking of the positive or adjusting means on the mark, typically making of adjustment necessary to bring operating characteristic in substantial agreement with the standardized scales or marking. And common mode voltage, this is very important in many of the like a converter inverter operation, the voltage that at a given location appears equal or in phase from each signal conductor to ground. And coupling, the associated of the two or more circuit or system in such a way that the power or signal information may be transferred from one system or circuit to the another circuit or system. Like a current transformer, you might have studied a instrument designed for the use in measurement of control. Why we define for measuring the current very large kiloampere current by the ammeter of very less ampere like a similar dropout, a loss of equipment operation, discrete data signal due to the noise, voltage sag or interruption, like electromagnetic compatibility, a measure of equipment tolerance to external electromagnetic field and ability of the device, equipment or system to function satisfactorily in electromagnetic environment without introducing intolerable electromagnetic disturbance to another anything in that environment. Electromagnetic disturbance, any electromagnetic phenomena that may degrade the performance of a device, a piece of equipment or a system. An equipment grounding conductor, the conductor used for connecting the non current carrying parts of the conduit, raceway and equipment enclosure to the grounding electrode at the service equipment and main panel or secondary of the your separately derived system. Failure mode, the manner in which the failure occurs, generally categorized as electrical, mechanical or thermal contamination. Then the frequency deviation, any increase or decrease in the power frequency from nominal we defined earlier, and duration of the frequency deviation can from several cycle to several hours. Then the ground. The grounds are used for establishing and maintaining the potential of earth or one of the conducting body or approximately that potential or conductor connected in to it, and the conducting ground currents to and from earth or conducting body. So, certainly you might have to talk about why we have a concept of grounding also. And grounding loop, a potential detrimental loop formed when the two or more points in electrical system that are nominally at a ground potential are connected by the conducting path such that either or both points are not at same ground potential. Like harmonics, we already define a sinusoidal component of a periodic waveform or quantity having a frequency that is not integral multiple of fundamental frequency. And harmonic component, the component of harmonic content expressed in terms of order of RMS values of the Fourier series terms describing periodic function like. And a harmonic content, the function obtained by subtracting the DC and fundamental component from the non-sinusoidal periodic function and deviation from the sinusoidal form expressed in terms of order of magnitude of Fourier series terms describing the wave and distortion of the sinusoidal waveform characterized by indication of the magnitude of the order of Fourier series describing in the way. Immunity, or you can call it the disturbance, the ability of device, equipment or system to perform without degradation in the presence of electromagnetic impulse, a pulse that begins and ends with a time so short that it may be regarded mathematically as infinitely, although the small area remains finite, and impulse is a surge of unidirectional polarity. Like isolated equipment ground and isolated equipment grounding conductors run in the same conduit or roadway as supply conductor, and this conductor may be insulated from the metallic raceway and all ground throughout the point. Isolation, the separation of one section of the system from the undesired fluctuations of the other section. Maximum demand, the largest of the particular type of demand occurring within a specified period. And momentary, when used in a modifier to quantify the duration of short duration variation referred to a time range from 30 cycle to 3 second. And momentary interruption, a type of short duration variation, and the complete loss of voltage less than 0 per unit or more than phase conductor for a time period of 0.53 cycles to 3 seconds. Like a noise, electrical noise is unwanted electrical signal that produce undesirable effect in the circuit of the control in which they occur. And nominal voltage, a nominal voltage assigned to the circuit or purpose of conventionally designed voltage like maybe 208, 120, 480, 277, 600, 415, 230. Non-linear a load that draws the non-sinusoidal current wave when applied to by a sinusoidal voltage. Normal mode, the voltage that appears differently between the two single wires and that acts on the circuit in the same manner as desired signal. Notes, a switching or other disturbance of the nominal power voltage waveform lasting less than a half cycle, which is initiative of opposite polarity, then the waveform is thus subtracted from the nominal waveform in terms of peak value of the disturbance voltage, and this includes the complete loss of the voltage for up to half cycle. Oscillatory tangent, a sudden non-frequency change in the steady state condition of the voltage or current that includes either positive or negative polarity. Over voltage, when used to describe a specific type of long duration variation referred to a measure voltage of greater than nominal voltage for a period of greater than 1 minute, and typical value may be 1.1 or 1.2 per unit. Phase shift, the displacement in time of one waveform relative to another of same frequency and harmonic content. Potential transformer, instrument transformer that is intended to have the primary winding connected to a shunt with a power supply circuit and the voltage on which the may be measured or controlled on the low voltage side. The power disturbance, any deviation from the nominal value or from the same selected threshold based on tolerance of the input AC power circuit. And power quality, the concept of powering and grounding electronic equipment in a manner that is suitable for the operation of that equipment and compatible with the premises wiring system and other connected load. Pulse, a wave that depart from an initial level for a period of long duration time and ultimately return to the original sag. A decrease in RMS value of voltage from 0.5 cycle to 1 minute and typical value 0.1 to 0.9. Shield, a metallic shield, usually copper or aluminum, applied over the insulation of a conductor or conductors for the purpose of providing means for reducing electrostatic coupling between the conductors so shielded and offers and others which may be susceptible to or which may be generating unwanted noise or field. And shielding, the process of applying conducting barriers between the potentially disturbing noise source and electronic circuit, and shields are used for to protect the cables, data and power and electronic circuits. And sustain, when used to quantity, the duration of voltage interruption refers to the time frame associated for long duration like a greater than 1 minute called sustain. And sustain interruption, a type of long duration variation complete loss 0.1 per unit of one more than conductor. And swell, an increase in RMS voltage or current form duration for 0.5 to 1 minute and typical value is 1.1 to 1.8. Temporary interruption, a type of short duration variation, the complete loss of voltage less than 0.1 per unit of one or more phases conductor, time period of 3 seconds to 1 minute. And total demand distortion, this is very important, goes to standard. The total demand, total RMS harmonic current distortion in terms of maximum demand load current, which is 15 to 30% minute demand. Point of common coupling, the point at which the electricity utility and the customer interface occurs, and typically this point is the customer side of the utility revenue meter. And total harmonic distortion, also called harmonic factor, the ratio of the true RMS value of the harmonic content in the RMS value of the fundamental quantity expressed as a percentage of fundamental tangent pertaining to degenerating a phenomena or a quantity which varies between the two consecutive steady states during the time period that is shared between short compared to the time scale of interest. Like under voltage, when used to describe the specific type of long duration, refers to measured voltage having a less than nominal voltage for a duration for a period of time greater than 1 minute and the typical value of 0.8 to 0.9 per unit. Like and voltage distortion, any deviation from the nominal sine wave of the AC line voltage. And voltage unbalance, the ratio of negative sequence or zero sequence component to positive sequence component usually expressed as a percentage in polyphase system. And voltage regulation, the degree of control or stability of the RMS voltage at the load, often specified in relation to other parameters such as input voltage changes, load changes or temperature changes. So, these were the some of the definition. We will talk about now power quality definition, some of them which are reported in different, different people have given a different definition for power quality. So, definition of power quality given in IEEE dictionary is power quality is the concept of powering and grounding sensitive equipment in a manner that is suitable for the operation of that equipment. And the IEC, that is we are talking about the standard, given that standard they talk about characteristic of electricity at a given point or electrical system evaluated against a set of reference technical parameter. So, electromagnetic compatibility is related to a power quality used with the International Electrotechnical Commission standard of 61000 to 11 state that electromagnetic compatibility is the ability of the equipment or system to function satisfactorily in its electromagnetic environment without introducing intolerant electromagnetic disturbances to anything in that environment. And recently power quality referred to the ability of electrical utility to supply electric power without interruption, and in general electric power quality referred to maintaining a nearly sinusoidal voltage to a bus at rated magnitude and rated frequency. Like so, what we cover like typically today the power quality definitions, terminology and the different terminology explanation about the typically the voltage power quality associated which is in the grid like or so. Typically we can call it like a power quality defined in different reference frame. If we talk about a majority of the literature is like a power quality in the typically power quality issues in the voltage or the grid like which affects really the different equipment and load. Another typically the concept of power quality in the load side when they draw the nonlinear current, because they also affect the voltage like also. So, you will find lot of literature and different books related to typically voltage power quality or current based power quality like also. So, both I mean if you look into with all these definition why we are defining, we will be dealing I mean what we will try to do in this course will trying to quantify with lot of examples, around more than 150 examples we like to consider the numerical examples which I tried virtually in my 20 years, and then we put in the kind of the books like. So, we will like to quantify with a lot of examples all these power quality, I mean not only mitigation, but the power quality issues, power quality definition, power quality improvement, and the different equipment used for power quality improvement. So, with this I would like to conclude, and thank you very much.